Okay, so this is just a quick supplemental note. Everything I'm about to tell you is stuff that we have actually already talked about in class, but I wanted to hit this point particularly hard. This is a very common mistake that lots of students make when doing vector calculus. And so again, I did talk about this in class, but I wanted to group all of the analogous scenarios together to make sure everyone's clear on the point here. Okay, so here's a scenario. Let's suppose we've been asked to compute a flux. And a little background information, it's going to turn out that the divergence is 0 and that the surface is an open surface. But maybe that's not given. So momentarily I'm going to scratch these out. And the scenario we're evidently starting with is just that we've been asked to compute a flux. Okay, so what a lot of students will do, very reasonably, they'll compute the divergence and get that it's 0. That's fine. Okay, here's where things go off the rails. Students will then think to themselves, oh, I remember a theorem that relates divergence to flux. That's Gauss's divergence theorem. And then they will write down flux through S, F dot ds, equals triple integral divergence, dv, which is, of course, triple integral of 0 at this point, which is 0, and then stop and think that they've gotten the right answer and walk away. And tragically, what they've written down here is all wrong. Now, why is this wrong? Well, students, of course, are thinking to themselves as they're writing this down, they're thinking, hey, I'm applying the divergence theorem. What's wrong with that? Well, here's the divergence theorem. Right, on our usual diagram. Very importantly, notice, to apply the divergence theorem, the surface has to be a boundary. Now, I know I've said this before, but again, I feel the need to hit this point hard. It's not a formality. It's not that it has to be a boundary as a sort of a technicality. In fact, it has to be a boundary of a solid, because whatever that solid is whose boundary defines the surface has to be the solid that is the domain for this triple integral. Right? So if there is no such solid, then there is no such triple integral, and certainly there is no application of the divergence theorem. Okay, so in this scenario now recall, and it wasn't necessarily explicitly stated in the question, but the background was that the surface for this flux is an open surface, not a closed surface, right? So this surface was, some surface, let's say kind of like that, just kind of a curved, like a piece of paper that's been kind of slightly bent in space. So this is not the boundary of anything. You'll notice that in the work that I've written down here, emulating what I've seen on student papers in the past, it's sort of glossed over what the solid for this, domain for this triple integral is. As it must be glossed over because, of course, there is no such solid. Right? So anyway, please be on the lookout for this. This is a very dangerous scenario, and if you fall for this temptation, again, when you see that the divergence is 0, and then you see, I see daylight, right? And it's very tempting to think that that this is going to work out as just awesomely, like this nonsense calculation seems to have. And then you step on the landmine, and again, nothing on this in this work is actually valid, right? So, in particular, let's just be clear about this. It's not equal to a triple integral because there is no domain for that triple integral, and so everything that follows, this is all just wrong. And even worse, it's not something for which I can really give much partial credit. If I were if I were scoring this question, really the only thing on the page that's right is that, the student has perhaps, the premise of this scenario is the student has correctly computed the divergence to be 0. So very, very dangerous in that it causes you to think you've got an answer when in fact you don't. And then you don't have the opportunity to actually solve the problem as it should be solved. All right, now there is an analogous scenario for line integrals. Very, very analogous. So let's suppose we're in this scenario here, and again, maybe the vector field is given, but the curl isn't explicitly, and the curve is given, but the fact that it's open is not explicitly stated in the statement of the question. It's just that we want to compute a line integral. And students will appropriately, reasonably, first thing, compute the curl and see 0. And then again, students will see daylight and think to themselves, oh, I remember a theorem that relates curl to line integrals. That's Stokes's curl theorem. And so students will, you can probably see this coming, but we'll write, okay, well then the integral over this curve of f dot dx is a flux of that curl. And of course that curl is 0, so we have a flux of 0, which again seems to appear to be 0. Again, very tempting. It looks like a good solution. It sure did work out great in terms of convenience. But again, nonsense, right? This, again, you notice I make the exact same mistake. I'm vague about what the surface is. And of course, now again, in this scenario, unstated but true side fact, our curve is an open curve. There is no such surface. Again, looking back to the diagram. Here's Stokes's curl theorem, and notice very conspicuously, in order for the Stokes's curl theorem to apply, we need for our curve to be a boundary of a surface. Again, not just as a formality, but because that surface whose boundary is our curve, we need it to be the domain of our new flux integral. So no anti-boundary, no flux integral, no Stokes's theorem. Right, so again, just like in the previous example, this is all garbage. This is all wrong. There is no anti-boundary surface. There therefore is no flux integral in the first place, and just everything that follows here is all wrong. Okay, so what we're seeing here is the importance, the great importance of making sure that if you want to apply one of these theorems, right, that is, if you want to apply it moving to the right, if you want to turn a lower dimensional integral into a higher dimensional integral, you'd better make sure that your domain is actually a boundary. Otherwise, it's not something that you can work with. Now, just as a third example, let's think about in the two-dimensional case. Let's think about Green's theorem. And so again, totally analogous. We have a theorem here, and if we want to move to the right, if I want to if I'm asked to compute a line integral, and I'm hoping to turn that into a double integral, well again, right here in the statement, you'd better make sure that your curve is a boundary. Because again, whatever region we're talking about, that region is going to be the domain for the new double integral. So in that next scenario, here we go. And again, as a background, it's going to turn out that Green's operator is 0 and that the curve is open. But again, stated is just that we're computing a line integral in 2 dimensions. I should say here in R2. And so, again, students would very reasonably compute Green's operator. Once they see that they've got 0, again, students might see daylight. Again, this happens a lot. I've seen this a million times. And then write, oh, okay, well, then the integral that I've been asked to compute by Green's theorem, so they're thinking, is a double integral of Green's operator. Note conspicuously absent is what the domain is. And of course, having computed Green's operator as 0, they again quickly, conveniently seem to have concluded that the integral is 0. And again, this is all wrong, all the same reasons. Again, there is no domain here. There is no anti-boundary for the curve because, again, background information, not explicitly stated, but the student didn't think it through. The curve is open. The curve is not the boundary of anything. There is no anti-boundary. There is no, therefore, double integral, and all of this work is garbage. Okay, so that's what I wanted to warn students about. Please, please, please be very careful about this. If you end up writing one of these things down, there's very little that I can give in the way of partial credit. And of course, I really want to give partial credit. So, it always makes me sad when I see students that step on these landmines like this. So, be warned, and hope this is helpful. Good luck to everybody as you're studying for tomorrow's midterm, and look forward to seeing you tomorrow. And of course, also good luck for everybody studying for the final coming up very soon. Okay, have a good day.